Thanks, Mark, for the introduction, and thanks to the organizers for having me. It's a real honor to get to speak here and to help celebrate Eric and Mike turning 60. So I was Martin's student, and Martin was Eric's student, so I guess I am Eric's grand student. And I think I might be the youngest descendant of Eric and Mike in terms of PhD date. That might be true. It's great to be such a part of such a big family, but yeah. So I mean, but I guess being so far flung, I don't have any, I don't have a whole slide deck of old stories to tell about them. But I guess I'm here sort of as a testament to their broad legacy, which is of course still under construction. So happy birthday, and yeah, thanks everyone for sticking out to the end, or end of today. Okay, yeah. So I'm going to talk today about repairing Reed-Solomon codes, and so this is some joint work with Venkat Guruswamy from CMU. Okay, so as you might have guessed from the title, this is a talk about coding theory, right? So it's right there in the title, I've got Reed-Solomon codes, regenerating codes, that's also a thing. Coding for distributed storage is a buzzword. It's very much a coding theory talk. And I know that some of you are thinking, it's been a long day. And those of you who are not in coding theory are thinking, oh my God, here come the parameters. There's going to be Ks and Ns and Ds, and what are they? There are going to be some. But I promise I'm not going to talk much about coding theory, actually. So I will talk a little bit about it. But really what this talk is about, it's about a fun problem about polynomial interpolation. And everybody loves polynomial interpolation. Yeah, that's right. So we're all going to enjoy this, even if you're not in the mood for coding theory after a whole day. Right, so what is the problem about polynomial interpolation? So let's recall sort of the very basic polynomial interpolation problem. So I've got some polynomial f. Does this laser pointer work? Yes. I've got some polynomial f. Let's say degree k minus 1 over some finite field. So for this whole talk, my field's going to have characteristic 2, so it'll have size 2 to the t. This doesn't actually matter as long as it has reasonably small characteristics, but it'll keep everything simple. So always f2 to the t for the whole talk. So I have this low degree polynomial. I have some evaluations of this polynomial. There they are. And I would like to learn the polynomial from some evaluations. And so here I am. I want to learn a polynomial. As we all know, I can do it by looking at k different evaluation points of this polynomial. If it's a degree k minus 1 polynomial, then I can do polynomial interpolation. I can figure out my polynomial. This is fun. Okay. In particular, whoops, sorry, go back. There we go. In particular, if I want to know not just the whole polynomial, but just f of alpha star, I can do the same thing, right? I can find k different evaluations, recover the whole polynomial, and in particular recover the one point that I'm interested in. Okay. So this is good, very standard. And we might ask, okay, so what if all I want to know is f of alpha star, just one evaluation point, but I'm not allowed to look at it for some reason? Do I have to look at k different evaluation points? Could I possibly get away with k minus 1? Right. And as many people are shaking their heads, and this stick figure is very sad, so like clearly the answer is no. No, we cannot get away with k minus 1 evaluation points. So the reason is that if k evaluation points determine my whole polynomial, but if I have only k minus 1 of them, this kth could be anything. And there'd be a legit degree k minus 1 polynomial that goes through it. Okay, so no, I learn nothing. I learn absolutely zero. And this is kind of important in, for example, crypto. This is used all the time, that I actually learn nothing about this last evaluation point. Okay, so we can't do any better. But this seems kind of unfair. Like, we really need k whole evaluations. All we want is one evaluation point. Do we really need k? That doesn't feel right. However, we all just nodded and said, of course we need k. We can't do any better. So what does this talk about? So here's the polynomial interpolation problem that I want to pitch to you guys as a fun polynomial interpolation problem. Take 2. Partial evaluations. So what do I mean by that? So same problem. Here I am. I want to know f of alpha star. For some reason, I'm not allowed to contact that. And I want to do so by downloading partial evaluation points. So what does that mean? Well, I might look at one of these evaluation points. Let's say that this is this is an element of a field of size 2 to the t. I can represent it as t bits. And so I can imagine downloading half of that, t over 2 bits. That's half a symbol. Okay? And similarly, from these other things, I could imagine downloading not, again, whole evaluation points, but just parts of them. And I could even, if I want to get really crazy, and I'm going to for this talk, let this sort of node here holding that symbol do some local computation, maybe add all the bits together, whatever, and send me just one bit back. Okay, that would count for one bit. And so the fun polynomial interpolation problem that I want to talk about today is the problem of how well can I do in this model. So once again, the problem is I want to figure out f of alpha star without looking at f of alpha star. And my goal now is not to minimize the number of points that I look at. We agreed it has to be at least k, but rather minimize the number of bits downloaded total. So that's the new goal. And just to clarify, so the bits downloaded, they have to be a function of what's in the node. This should be non-adaptive. Obviously, the function will depend on the node that was erased, but the other nodes can't talk to each other. So that's the polynomial evaluation problem, or that's my new interpolation problem. Make sense?
So you get to pick which bits?
You get to pick which bits, but the bits can depend on alpha star, but that's it. So for every alpha star, there exists some function of bits that you can set. That's right. Okay, so that's the problem. So now let me explain why we might want to think about this problem, other than it's kind of fun. Maybe you can do better. Spoiler alert, you can do better. So this problem actually comes up in distributed storage. So in distributed storage, the setting looks like this. You've got some file f, and you want to distribute it with redundancy between a bunch of different nodes, which look like that. And there are two sort of salient things about this picture that will concern us for this talk. The first is that nodes can fail. That's what it looks like when a node fails. So it becomes unavailable for the foreseeable future. And the second thing we need to know is that communication between nodes can be costly. And this is actually the case in sort of modern distributed storage systems. We have all these cheap computers. Many of them fail all of the time. So nodes can fail and do fail. And the communication is expensive. So these things are like big warehouses kind of spread apart. And actually, in some of these systems, the bandwidth is really a non-trivial amount of the cost. So we'd like to minimize that. Okay, so slightly more formally, so this is still a cartoon, but we're going to treat this file f as k message blocks. So each block stores, let's say, a byte, or for us, let's say, an element of f2 to the t. And these k message blocks are encoded as n nodes, n encoded blocks, which also just stores the field element over the same field. You can play with this assumption, but for now, that's what they do. Okay, and we want to encode this with redundancy so that the things that we wanted on the previous slide hold. So in particular, a node might get destroyed, and we want three things. So we want to tolerate many node failures. So it might be that not just one node gets destroyed, but many. We would like to be able to handle that. We never want to lose data. That would be bad. That said, we also don't want too much storage overhead. So n should not be much bigger than k. That would be very wasteful. So these two are sort of the traditional trade-offs that one has in coding theory, robustness versus overhead. And then we have this other thing, which is that we want to be able to reconstruct one failed node quickly. So it turns out in a lot of these systems, the most common failure case is that exactly one node fails. Actually that is like 98% of the time, and there's some Facebook data set that says that exactly one node fails. And so we'd like to be able to handle that case extremely quickly. Maybe this other one where many nodes fail, we can take a little more time on. But the most common case we'd like to be able to handle extremely quickly. Okay. And so for this talk, these two things, tolerating many failures and not too much storage overhead, like I said, those are sort of the traditional things one wants in an error-correcting code. And we're going to use a traditional notion, which is a maximum distance separable code. So that's just some jargon, but all it means is that any k nodes determine the file. So if I go to any k of these n encoded blocks, I can get my whole file back. Okay? And we can get that. We know of codes that do this. That's clearly the best you can do, and so we want that. So we want to be able to have the best possible trade-off here. And so the rest of this talk is about the question, suppose I enforce the best possible trade-off here, what can I do about that? And how do I measure quickly? Well, as you might have guessed from the discussion so far, it's going to have something to do with communication. And we'll formalize that a little more in a second. OK, so that's distributed storage. So one way that distributed storage is done in practice is Reed-Solomon codes. So Reed-Solomon codes are a very classical coding scheme. They've been around for a long time. and they are implemented to provide this sort of redundancy, for example, in distributed storage. So here's how they work, if you haven't seen it before. So basically, this is where the polynomial interpolation part comes in. Reed-Solomon codes are just about evaluating low-degree polynomials over finite fields. So I have here my file, and remember, my file was just a bunch of blocks, so k different blocks, k different field elements of my big field. And I'm going to treat it as a polynomial. So I'll take these k different field elements, and I'll treat them as coefficients in some k-1 degree polynomial. And then how do I take my file and put it on the nodes? I'm just going to evaluate this polynomial at n different points. There we go, like that. Okay, so I take n different points, alpha 1, alpha 2, all the way up through alpha n. And for all of this talk, you can actually imagine that n is just the size of the field. So these are just all of the points in the field, and n is 2 to the t. It's a good thing to think. Okay, so I take all of my points in the field, I evaluate f on all of my points, and I slap these evaluations onto the servers. Okay. So now, does this have the properties that we want? So pretty easy to say yes. So for example, any k nodes determine f, because I can do polynomial interpolation, right? If I have this degree k-1 polynomial that is my file, then any k nodes, that's k evaluation points, gives me the whole file back. So good on that. And if one node happens to explode or become unavailable, indeed we can fix it, right? So just set up a replacement node. Like any k nodes determine the whole file. They determine what I want. We're good. Okay. So that's the scheme. It works. How well does it work? Well, so here are the things we wanted, right? So any k nodes, any k blocks determine the file. We got that. And then the second thing, which is a bit more nebulous, right? We want to repair a failed node quickly. Well, how well do we do on that? So, as you've probably noticed, this is just the straightforward polynomial interpolation problem that we had at the beginning. Right? I'm downloading k whole blocks in order to recover just one block. That is expensive. We would like to do better. Okay. So can we do better? First time we'd ask this, we all say no, we can't do better. We need to contact at least k nodes. So answer is no. Frowny face, on the other hand, that means it's optimal. Yay. So, that's the plus side. And in fact, this solution, this optimal solution, is used not just in theory. This is used in practice. For example, the Apache Hadoop distributed file system uses Reed-Solomon codes with exactly that algorithm in practice, the one that I just showed you. So that's how it works. Okay, so Reed-Solomon codes for distributed storage, that's what this talk was about, right? So these are a nice solution. They've been around for a long time. They're actually implemented. And we just saw that this is optimal. Right? Okay, so talk's not done. Obviously, we'd like to do better than optimal. And hopefully the polynomial interpolation problem that I showed you at the beginning is a hint as to how. So the way is through something called regenerating codes. So regenerating codes have been around maybe 5 or 10 years. I would point you to this survey by Alex Tomakis and others, which is a really great survey for sort of the history. And the main insight of regenerating codes, which is sort of a very clever insight, is that minimizing the amount of data downloaded, which is actually what we want to do for this task, is not necessarily the same as minimizing the number of servers that we contact. Because in real life, we have this freedom to not download an entire disk or an entire block, or however you're actually implementing this, entire stripe. Instead, you can download just part of it, and thus sort of save on bandwidth. Okay. And so this leads to this polynomial interpolation problem that I showed you before, right? So I have this setup that I had before where I was contacting k different nodes, downloading all of the contents from all of them. Remember, there are t bits per node. My field has size 2 to the t. Right. So instead of saying that the cost of this scheme is k nodes, instead I'm going to say the cost of this scheme is k times t bits. And I'm going to ask, can I do better by minimizing the number of bits sent? So this is exactly that polynomial interpolation problem that we saw at the beginning.
But you are allowed to query more than k nodes.
Yes, and in fact you must. Yeah, that's right. You're allowed to query more than k nodes, and you hope that somehow by querying more but downloading less, then on net you can benefit. That's the goal. So just slightly more formally, so this is called the exact repair problem in regenerating codes. So what I'm posing is the exact repair problem for Reed-Solomon codes, or what I'm posing to you. I was not the first person to pose this problem, but this problem is called the exact repair problem for Reed-Solomon codes. Here's the problem, right? F is a degree at most k or less than k polynomial over f2 to the t. some node I fails. And then each other node has knowledge of I, the index that failed, and is required to sort of non-adaptively, without any communication, return some message. And the goal is that these responses should determine, deterministically, the value that I wanted. And the cost that we're going to measure is called the bandwidth. And this is just the total number of bits returned in all of those yellow speech bubbles, the total number of bits returned. I would like to minimize that. So this question works in general. This is the exact repair problem. I'm actually going to focus on the exact repair problem where everything in sight is linear. So in practice, all of the solutions that we have are linear. And it also makes the analysis easier. It also allows us to prove tight upper and lower bounds, which we wouldn't be able to otherwise. So that's another reason why I'm going to do that.
Would the answer differ if you're not restricting to linear?
Say again?
Do you know what happens if you allow general functions?
I don't know. So I'm going to show you a matching upper and lower bound for linear, and the lower bound won't hold anymore if we relax linear, and I don't know if you can do better without it. So by linear here, I mean the code is linear, and then I also mean that these functions, these g's, are linear, and that sort of my way that I add them back up is also linear. Yeah, and without those assumptions, I'm not sure. Our scheme will be linear, but our lower bound won't hold anymore. Yeah.
You could ask, given the way you are measuring, maybe it's not relevant for the applications, but for your fun interpolation problem, you are actually building a bigger code, right? Because each of them are.
That's right.
And you can ask to recover any T bits, not necessarily the T bits in a block.
That's right.
So was this looked at, or?
So you mean right? So one way of seeing this is saying, okay, I'm going to take this code. Basically, I'm going to concatenate it with the Hadamard code, right? Look at all the linear functions, and then I'm taking.
No, I'm not suggesting a solution. This framework allows you to recover some T bits, particular. But you can ask to recover other T bits and ask.
Well, not necessarily T. You can recover some bits from here, some bits from there.
Exactly. So, but let's say T just to measure it. Yeah. So some number, and what it looked at, just not to recover something in a block.
I see. That's a good question. So if you allow for arbitrary sets of bits, that's probably just the same as locally decodable codes, right?
Sounds like locally decodable.
But then if you...
But it's sort of an amortized version because...
Right. Yeah, so I guess batch codes are something that's like that, which is sort of trying to amortize the queries. So actually, there is some work on that, and maybe we could talk about it offline, because that's a very good question, and I think there's a lot of interesting work about that. For arbitrary sets, I'm not so sure, but certainly for specific sets. Yeah. Okay. Any other questions at this point about the problem statement? Cool. Okay. So the question for this talk is. Here's the question. Can we do better with Reed-Solomon codes? Can we do better than the naive thing, which is just contact k different nodes, download t bits from each? Okay, so this question was first asked by Demox et al. In 2010, and actually there's been a little bit of work on it before. So Shanmugam et al. Have this really nice paper from a couple of years ago where they show that the answer is yes. That in fact, so they come up with certain specific examples of Reed-Solomon codes, like a length 5 and a length 6 code, and I think a length 14 code, where they can come up with schemes that work better than the naive one. And I found this extremely surprising, because I was always raised to believe that you need k evaluation points.
Even for linear functions, it's not the 5-degree one.
Right. Yeah. So they found. Exactly. So I was really surprised by this. So this led us to start looking at it. And what this work is, this is joined with Venkat Guruswamy, is that the answer is yes, you can do better with Reed-Solomon codes. In fact, for infinite families of examples, and in fact, you can do optimally among any MDS code, where again, MDS just means this property that any k can recover the whole file. So Reed-Solomon codes, which are already used in practice, in fact, are optimal. So that's a nice punchline. I like that. There's some other things wrong with them, but let's gloss over those and stick with the nice punchline. Cool. And so more generally, we don't just give an answer for Reed-Solomon codes, it applies more generally to any MDS code. And one of the big differences between this and previous work is that previous work designing regenerating codes really treats the the contents of a node is a vector, so it picks a basis and deals with these sort of in that basis very explicitly, which has led to some really, really beautiful work and some very clever codes. But it doesn't sort of give a natural way to analyze codes that we already know and love, which are sort of basis-free, defined over a big field. And so our work gives a framework to sort of think about those. Cool. So let me just tell you one punchline. So like I said, there's a more general theorem, but how am I on time?
Yes.
Yes, good. That's what I like to hear. Yeah, let me just give you one punchline of the general theorem, which will give some sort of an answer to the polynomial interpolation problem that we saw at the beginning. So here's an informal theorem. If you take a Reed-Solomon code with k equals n over 2, so the degree of the polynomial is half of the number of nodes, okay, and you have n evaluation points where n is just 2 to the t, so all of the evaluation points in the field, nothing special. Then you can get bandwidth n minus 1 bits, and this is optimal. Okay, so let's sort of look at this for a minute and do some arithmetic. So there are n nodes, one of them is down, so n minus 1 bits is 1 bit per surviving node. Okay, so I think that's pretty cool. So this can be compared to the naive scheme, which remember was t bits from k different nodes, which in this case, working out this n equals 2 to the t and k equals n over 2 is about n log n. So it's moving from n log n to about n. So better. Yeah.
So what are your quantifiers? That these single bits that you pick from each, is it like so for every choice of those single bits, or you have?
It is not. It is there. Yeah. For every node that can fail, there exists a choice of bits, so that you can recover. Yep.
And it's easy to compute.
Yes, I mean they're going to be a linear function. So yeah, very easy to compute. Okay, so this compares well with the naive scheme. It actually also compares well with the best known scheme in this parameter regime for that existed already. Although, sort of in fairness, this is kind of a strange parameter regime for regenerating codes. But so Reed-Solomon codes are the first known optimal code for this, even though they've been around since the 50s. Okay, and just sort of recasting this in our polynomial interpolation problem. So here's our poor little struggling person who wants to know f of alpha I. What this says is they can download just 1 bit from all the other nodes and recover that. When k equals t over 2. Or sorry, when k equals n over 2. You can generalize that, but this is going to be the cleanest. So I'm just going to talk about this for the remaining 10 minutes. 10-ish minutes. Cool. Okay, so that's what I want to do for the rest of the talk, is tell you how to do this. So it's kind of a magic trick. Okay. So I'm going to need one tool, which is the field trace. If you've not seen this before, here it is. Or if you have seen it before and need a refresher. So the trace of f2 to the t over f2 is just defined like this. So it's this polynomial, x plus x squared plus blah, 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 plus x to the 2 to the t minus 1. Okay. This might look like slightly arbitrary if you haven't seen it before, but all you need, too fast. All you need to know about the trace is these two important things. So the first is that this function is f2 linear, which means that trace of a plus b is just trace of a plus trace of b. And also it takes in an element from the big field, and it spits out an element of f2. So it spits out a 0 or 1. And the other thing we need to know is that all f2 linear functions from the big field down to f2 look like trace, basically. So they all look like phi of x equals trace of something times x for some gamma in your big field. So you can sort of just think about it like a generalization of inner product. So it's just sort of captures all linear functions. Okay, so with that in mind, here's the scheme. Okay, so once again, I'm going to fix these special parameters just to make it like as cute as possible, but it generalizes and gets slightly less cute along the way. So let's set k equals n over 2, like we had before, and n is 2 to the t. So n is the whole field, so all field elements represented. And let's just say, for simplicity of notation, that f of 0 fails, although this works with if any fails. So what are we going to do? So I'm going to start by just writing down some true facts, and then we will arrive at a scheme. So fact 1, this fact, which you might have seen before, for any polynomials f and g with degree less than n over 2 over a field of size n, if I sort of take the inner product of these polynomials, just sum them up over all the elements of the field, I get 0. Okay? So If you haven't seen this before, believe me, it's true, and you could work it out. So this is just sort of a true algebra fact about low-degree polynomials. And now I'm going to choose a function, g. I'm going to pull it out of a hat. So here it is. Here's my function. G depends on a choice of zeta, so I'm going to pick a zeta in my big field, and I'm going to define g like this. It's the trace, which we saw on the previous slide, was that big polynomial, divided by x. Okay. And so it's not apparent looking at the top thing there that g is a polynomial, but it is. If you simplify it out, it looks like this. So this is what g is. Right, so I'll just pick it for now. And the only things we need to know about g are these facts. So here are some facts about g which are easily verified. So the first is that the degree of g is less than n over 2. Okay, this is demonstrably true. Good. G of 0 equals zeta. This is also easily checked. I just plug in 0. All I have is this constant term zeta. And now imagine I plug in any alpha j that's not zeta. So what do I get? So now let's go up and look at this expression. So if I plug in alpha j, then on the bottom I get an alpha j. That's easy. And on the top, I don't know what I get, but I get either a 0 or a 1, because that's what trace spits out, is 0 or 1. Okay, so what I have is that I can take g to be this g, so this low-degree polynomial. I'll take f to be the polynomial that I would like to recover, and take this expression and put it together and move the 0 term to the other side. So I've done this all at once. So g of 0 is zeta, so that's this zeta. And then this whole sum was equal to 0. So I just moved the 0 term to the other side, and I didn't care about signs because I'm working in characteristic 2. Just hooray. OK, so here's an expression. Is everyone good with this expression?
Yeah, j different value in the j different with 0.
Oh, sorry, 0. Yeah, that was a, yes, j not equal to, alpha j not equal to 0 should be the index. Good. OK, so here we have an expression. And I'm going to take the trace of both sides. Okay, so and trace, as we discussed, is f2 linear, so I can move it inside the sum. And I can also ignore this 0 or 1 thing. OK. So that's an expression. And I claim that this is the whole scheme. Now we're done. So let's see why. The algorithm is that I'm going to query from fj this one bit. So I'm just going to say, hey, fj, or node j, give me this one bit. And notice that this doesn't depend on zeta. So I'm just going to do this once for each node. So that's my one bit from each node. This is the bit that I download. And then on the other side, well, this has a zeta in it. So if I have these 1 bits from every node, then I myself, on my own, pencil and paper, can reconstruct these with this 0 or 1 that depends on zeta. I can figure out what that is. So for every single zeta, I can compute this quantity. But if I can do this for every single zeta, then that's just an arbitrary linear function of the thing that I want. If I can get, for example, a whole basis's worth of these, then I learn the thing that I want. Okay, so that's the algorithm. I'm going to assemble my collected bits, 1 from every node, to recover an arbitrary linear function of f of 0. I'm going to do this t times for t linearly independent zetas, linearly independent over f2. And I'm going to recover my evaluation point. Okay, so that's it. That's the scheme. And that gives us this thing that I was promising you. I look at 1 bit from every other node, download it, and figure out the node that was missing. And this makes little stick figure person very happy. So that's cool. And there's sort of an easy variant for this. If you want to make it not make k different from n over 2, you can actually get a high rate code by just tracing out over a bigger subfield. So the same scheme, but just different subfield. And what you get if you do that is you get a rate 1 minus epsilon code. So that means k is 1 minus epsilon times n. So the overhead is very small. And the amount that you download from each node, instead of being 1 bits, is about log 1 over epsilon bits.
So what happens if k equals 1?
K equals 1, so for linear function.
You would ask 2t bits in the trivial algorithm. How many bits do you ask?
So this scheme actually only works for k bigger than n over 2.
Bigger than?
So the reason is because for the algebra to work, it needs to have subfields.
No, sure, but Or you mean?
So I'm not saying that it's impossible in general. I'm saying my answer doesn't cover that. Yeah, that is a good question.
The T is N, and 2 to S is a divisor of T, so
Yeah.
it's very close to that.
Okay. Yeah. So yeah, T/4. Okay.
Yeah, but
T/4. Yeah.
but I think that yeah, let me think about the k equals 1 case. I feel like there should be something you can say there. But yeah, our thing doesn't work. But yeah, was there a question in the back? Yeah.
That's why f alpha is represented somehow like with t bits, right? But the bit you need is not one of those t bits.
That's right.
But it's some kind of like linear combination of those.
That's right.
So what is the use of that? Because then actually to learn that linear combination, you have to download all of those in order to find out the value of the linear combination. Right? So
Yeah, so that's a very good question. I've got a hidden slide for that. Here it is. Yeah, so the question is, wait, hang on. I need to, like, the bits that I return, the function that I return depends on the identity of the node that failed. It takes me t bits to say what node failed. So don't I need to send each of my k nodes t bits? Isn't that back to the naive scheme? That's the question? Yeah, very good question. That's legit. So in practice, the reason that we only measure, or that in the storage folks only care about the downloaded amount rather than the communication going from the client to the servers is because it's actually implemented like this in like a striped fashion. So what's this picture? Right. So my original file. Maybe instead of thinking of it as original file, let's think about it as m different files. So I have like m different low degree polynomials, and I still have n servers corresponding to my n evaluation points. So like this is the alpha 1 server, this is the alpha 2 server, this is the alpha 3 server, and so on. And I'm going to stripe this scheme across these different servers. So this alpha 1 server gets all of the polynomials evaluated at alpha 1. And so now what happens when server alpha star fails? I need to tell each of these n servers, hey, alpha star failed. So either I can just broadcast it and it's free, or I have to actually tell them, in which case it is k times t bits. But then what happens is that they return to me whatever they would have returned to me before, multiplied by m. And in practice, m is like really, really big. And so the amount of communication that I need to talk to them and just to tell them, hey, alpha star failed, is swamped by the communication that's coming back. So for this application, that doesn't matter. However, I think that's a really interesting question that, that I don't know the answer to, is what happens if I want to sort of minimize communication in both directions? And I don't know the answer to that. So I think that's a really good. Okay. Thank you for letting me reveal my hidden slide. It makes me feel proud. Okay, now I'm probably almost out of time. Yeah. Okay, so let me wrap up real quick, and then I can answer any more questions. But so it turns out that all linear repair schemes actually look like this. That is to say, if I have a good linear repair scheme for Reed-Solomon code, then I can come up with a bunch of nice polynomials. That's those G's. And so we just saw that if I come up with a nice G, then I get a nice linear repair scheme. Turns out this completely characterizes things, and this is where we heavily use the linearity assumption. And so that's cool because it allows us to prove a lower bound. And in fact, the lower bound is exactly matching, like even up to the leading constants, which I think is like the first time in my life that I've proved a lower bound that matches up to the leading constants. So I'm very proud of that. So yeah, so that matches, and it generalizes to general MDS codes. So just punchline. Yeah.
That's good.
Yeah. So the generalization from nice polynomials is nice dual code words. Yeah. Cool. Yeah. So punchlines. So we just saw this rate 1/2 code with 1 bit per node. This generalizes to high rate codes. This is actually even optimal among MDS codes with linear repair schemes. And we also sort of give this nice framework. So it means that to come up with other trade-offs for different setups, different choices of evaluation points, you just need to sort of come up with a nice family of polynomials. And in fact, in exciting recent work, Ye and Barg gave a nice family of polynomials for a different parameter regime. So I was always talking about in this talk. N is 2 to the t, so that's the whole field, which means that the number of bits per node is like log n. But you might be interested in a different parameter regime where the number of bits per node is much bigger than n. And so they managed to choose some evaluation points very cleverly and come up with some nice polynomials using our framework to show that actually Reed-Solomon codes are optimal in that parameter regime as well. And let me just finish up with some open questions. I think maybe for purposes of time, I'll just mention the last one, which is my favorite, which I think that this is a cool polynomial interpolation fact, and it should have other uses. And so I'm just telling everyone I can about this polynomial interpolation fact, and I hope that someone else can come up with something cool to do with it. So with that, I'll end. Thanks.
Any questions for the speaker?
You always need, so in this case, the number of bits you have is still sort of linear in the cases parameters with sublinear bits without taking all bits.
Yeah, that's right. So that's what this, so I mentioned there's these two different parameter regimes. So in the parameter regime where t, the number of bits per node, is quite less than k, which is the dimension of the code or the degree of the polynomial, it's not hard to see that k is a lower bound. So if k is much larger than t, then the amount of communication I need is going to grow with k. On the other hand, in this other parameter regime, when t is much bigger, then t is the relevant lower bound. And this work of Ye and Barg that I was citing before shows that Reed-Solomon codes in that parameter regime as well can have communication that grows like t, which it feels right because you only want to recover t bits. Yeah. So,
If there aren't any other questions, why don't we thank the organizers for it?
Yeah.